So welcome everyone to the second session on modified cosmology and gravity theories. So first speaker of the session is Sadam Leonardo Kap from the Indian Institute of Technology in Kanpur, India. So Sadam, whenever you want.
Thank you, everyone. My title of talk is Modifying the Standard LambdaCDM, a non-minimal coupling between dark matter and K-essence scalar field. The talk would be more theoretical. So first of all, we start writing an action for this non-minimal coupling feature between dark matter and some scalar field, which is driving this cosmic acceleration. So first term we are having the first term with the Ricci scalar R is Einstein-Hilbert action. And in second one, we have a dark matter fluid model given by Brown. It's action for the perfect fluid. And you can see over here that there is a rho, which denotes the energy density of the fluid. And it's a function of number density and entropy density. And we have this J mu, the flux density, which is contracting with some Lagrange multipliers, this phi, s, theta, beta, and alpha. So these are Lagrange multipliers, and these commas are actually giving the space-time derivative, a covariant derivative over here. And because these are scalar, then it becomes simply partial derivatives. So these Lagrange multiplier, we can have some physical, meaning. For example, this theta becomes the gradient of temperature. Similarly, we have phi, it becomes gradient of potential, and we have this entropy. On the other hand, we have alpha, which shows that the Lagrange fluid coordinates. Then we have some K-sense Lagrangian, which depending on some field that is a phi, and the kinetic term, which is actually half phi dot square. And for the K-sense field, the Lagrangian have some non-canonical type of structure because its potential is multiplying with kinetic term, and this kinetic term has some x and its higher power, so minus x plus x square. And so if we are taking this action up to over here, then this the dark matter and the scalar field are minimally coupled to gravity. So now we are adding some different interaction type of Lagrangian, which makes this whole system as a non-minimally coupled. And therefore, we are introducing the interaction like this. So we can have some interaction function that depends on the number density, the entropy per particle, entropy density per particle, the field phi, and its kinetic component. So it's actually showing that some interaction is going on between the dark matter and about the scalar field, which is actually candidate for dark energy, and they are always minimally coupled with the gravity. So it's some kind of non-minimal effects between the matter fields. On the other hand, we can also introduce something so that this action is remain a scalar quantity, which is so interaction function f, and then there is a particle flux density is contracting with the field velocity j mu d mu phi. So we are introducing it. Maybe it can give us some nonlinear behavior during the matter epoch, and it may have some deviation from the LambdaCDM standard model of cosmology. On the other hand, we have a different scenario where the interaction function is multiplying with Ricci scalar in that way that we have modified the matter sector. But at the same time, there is the modification that takes place in the matter sector also induces some change in the curvature part. So such modifications has simultaneously change in both the gravitational sector as well as the matter sector. So these are some form of non-minimal coupling between the matter and the gravity part. So we have seen that what could be the effect of this L interaction in our system. Then we can see in that the Friedmann equation changes because of some additional term, which is as rho interaction, as well as the second Friedmann equation changes because of this P interaction. So we have this rho for the dark matter fluid, rho phi for the K-sense fluid, so K-sense field, as well as the interaction term that is coming from this L interaction. On the other hand, we have also the field equations also modified. If you vary the action with respect to the field gets modified because of these interaction parameters. For example, f, we have several derivative terms and so on. And this first this first equation also provides constraint on this dark matter fluid, because if we are just dividing with respect to 3h squared, then we can have this omega m, the fractional fluid density. So the first equation will provide us with the constraint on the evolution of dark matter profiling. Now we can study with the system's qualitative behavior, but in general we cannot study this. We have to introduce some model. So here we are introducing a kind of toy model in which the interaction depends on energy density, some field phi, and the exponential to the power kinetic term. Now this kind of interaction has some all the parameters like epsilon, m, and beta. So our job is to first constrain this one. Therefore, we have chosen to use the dynamic system stability, since we are not explicitly working on any data. Now, since our system is non-minimally coupled, therefore we have to consider it as a whole system. So we have defined the equation of a state, which is defined as the ratio of pressure to the energy density. And for the quiescence field, we are considering the potential of the quiescence field to the inverse power to the power of phi square, inverse power law type of potential. And then we have the pressure, so the propagation of pressure in the field as well as in the fluid. So the CS squared is basically give us that what is the speed of pressure perturbations in this whole system. And it has to be always between 0 to 1. It's the causality limit. It cannot be negative. If it's negative, then the model is not producing a stable kind of solutions. So first of all, by using the dynamic system analysis, we are getting some critical points. And for those critical points where we have some finite interaction, we have found that the equation of a state becomes epsilon and m parameter dependent. And here we can see the behavior of those critical points, in which the green region shows the accelerating regime where omega total lies between -1 to -1/3. On the other hand, the blue region shows the phantom behavior where the equation of the state is crossing -1. So we see that when we are closer to epsilon to the power minus, let us say 0.1, 0.3, and so on, and very close to m negative, then we are having this acceleration close to -1. So this is constraining epsilon m. On the other hand, we are trying to see that if we are picking some parameters, then our model is stable at the background level or not. Therefore, we choose some point between epsilon and m, and then we have constrained this beta, the other parameter of the interaction, as well as the potential parameters. And in the blue region, we are seeing some stability of the model, that if it is stable, then it lies on blue region. On the other hand, we have some certain conditions that if the universe is entering at the late time cosmic acceleration, then the field density must be dominating with the sound speed that it must be always positive. So this constraint is shown by this pale yellow region, on which we are constraining this beta and delta. So we have in that way for different epsilon and m, in such a way that our model is producing enough acceleration, as well as this fractional field density must be dominating in the late time cosmic era, as well as the sound speed must be in the perfect limit, in the positive limit. So now we have also seen some qualitative behavior. In the left, we are plotting the phase space of the system. The phase space is three-dimensional, where x and y is representing the field parameters. On the other hand, the z is capturing the interaction parameter. And here we are getting some kind of critical points: A1, A2, A3, A4, and 5. So A3 is some kind of phantom point, and in which the interaction vanishes. So some trajectory which is originating at some point in the phase space ending up A3, but it is non-physical because sound speed at A3 becomes negative. So we cannot consider it as a significant critical point. On the other hand, when we are seeing that in the left portion, where the trajectories are originating but ending up with A5. So A5 is a critical point where we can see some acceleration or phantom kind of behavior. With that, the model is stable and all the trajectories are ending up at A5. So the qualitative behavior, we can see some parameters evolution from past to present and future. So here n is the logarithmic of scale factor, and the negative n is actually showing us the past epochs, where we have plotted the fractional field density sigma square denotes the matter fraction density. Omega total is total equation of state of the system, and sound speed is the sound speed evolution. Now, when we are seeing at the past, we are seeing that the case intensity is dominating in the past. It's actually a behavior of the cases that although it is minimally coupled, non-minimally coupled, it can mimic a radiation kind of characteristic. So you can see that in the past, when quiescence is dominating, the green line, which is showing that omega total, is starting with 1/3, and at this point, the sound speed is also 1/3. So it's kind of the quiescence has some inbuilt characteristic that it can mimic the radiation epoch. So as we are progressing towards current epoch, the red line, which is denoting the fluid density, the dark matter profile density, then it is dominating on and over here in this region, the quiescence density is subdominant, and as we are progressing towards the present epoch, then again the quiescent density dominates, and the dark matter profile gets diluted, and we are entering at the late time cosmic acceleration given by omega total is minus of 1. So this is it. Thank you. So we have taken just only a fluid model, so for interacting model for this one type of interaction, and I also noted that if you are choosing same type of interaction for this particular second type of interacting non-minimal coupling of effect, we are getting the same result. On the other hand, we have studied this kind of interaction where there is a curvature coupled type interactions. We have studied with the quintessence, and it has some different result. So I think, can I finish? Thank you.
I mean, I want to start with the question regarding your model. Like, you're sort of proposing a modified version of the standard model. So I was wondering, how does this modification, or how does this new model address some of the main problems that LambdaCDM has? What kind of effect would it have on these things?
Recently, people have shown that if you propose some interaction between dark matter and dark energy, then the Hubble tension apparently can be resolved. So in this case, we are actually seeing some kind of effect, although we have not studied with the data yet, but in our current study, we are going to study some things. So it is our model is a feature more dynamical thing, and we don't know anything about dark matter and dark energy. So if the Einstein's gravity is correct and all this model that, okay, maybe there exists dark matter and dark energy, then still we have more room to take consideration that there could be some kind of interaction. So we are just seeing that, okay, if there could be some interaction and we can study from the action principle, then what could be the effect that we can see? We are not saying that our model it's like a toy model, but we have to we have to test with the data.
Okay. Thank you. So are there any questions about the talk, or?
Pavel is raising his hand.
Oh, it's not showing in my computer, but yeah, sure, Pavel, go for it.
Yeah, hello. I'm not visible, am I? So the question I had, Saddam, was because you just mentioned that you need to test the model, right, against data. So one immediate test would be this test I mentioned on the existence of dark matter, right, with dynamical friction. So in order for your approach or the approach of investigating some coupling between dark matter and dark energy to be viable, one would have to show that this coupling eliminates or reduces this dynamical friction significantly. This is a very strong condition, I think.
Okay.
So, because otherwise if dark matter is just free particles, then it's ruled out by the non-existence of this Chandrasekhar dynamical friction.
All right.
So that is a strong.
Yeah, I will definitely see those papers and try to test these. Thank you so much.
Okay, so Indra also has a question or a comment.
Yeah, no, I had a question. So I guess like much of what you're talking about is at the background level, but regarding the growth of structures in the universe, do you think your model can address the kinds of observations that I was talking about regarding these very significant underdensity or the overmassive galaxy clusters at high redshift? Would you be able to address these things?
Yeah, we are definitely working on that on the cosmological level, and some paper written by Boehmer. They have also been taken same framework, and they have worked with the quintessence, and they have shown that the structure formation is consistent with this approach, non-minimal coupling approach. Then, but we have not yet tested with quiescence or maybe some version of other field. But I think it definitely will, because we have a general structure, and maybe some form of interaction can cope up with these cosmological perturbations data.
So
And
you might be able to enhance the growth of perturbations.
Yes, it may be, depending on the model.
Depending on the model. Thank you.
Yeah.
Thank you. So Asher also has a question.
Yes, thank you. Now, we have a problem, right? We have in cosmological theory two unconfirmed ingredients, which are dark matter and dark energy. And I suppose most people here don't believe in dark matter.
Yeah.
So, but what you are suggesting is to replace those unconfirmed components with an unconfirmed field, which looks very much ad hoc. So can you comment on that?
Yeah, we have the evidence that scalar fields may exist because we have Higgs field, and Higgs is a scalar field. So on that basis, and also we have inflation, right? That if we have a scalar field, and a scalar field can mitigate the inflationary epoch in the early universe. So these are some motivations where, although these are very ad hoc term, but again, there are a lot of different cosmological data which are actually work with this quintessence model as well as quiescence model, maybe some ghost models. So yet we don't have a concrete proof, but it's the way we are actually progressing that for unknowns, we can parameterize things and we try to see what happens.
Thank you.
Yeah.
And Roberto also has a question.
Yes, a few. This method of non-minimal coupling could be also applied for relativistic MOND theories, Saddam, like the vector and
actually,
tensor.
Yeah.
Yes.
Yeah, actually, I haven't yet started with MOND, but maybe if we have some specialist on MOND, so maybe they can comment that can we have some junction between this non-minimal feature or maybe MOND. I have not yet worked with this scenario, so maybe.
Yes, excuse me. Thank you for the presentation. I have a small question. If I understood well, it's algebraic work only. Is there any physical motivation for this algebraic work? You are talking about phi, what is phi physically, for example. And okay, that's my question.
The motivation comes from this Hubble tension, that we have ongoing Hubble tension and maybe some problems with structure formation and so on. That's why we introduce this non-minimal coupling effect, and people have also studied some different feature to address those things. So our ways are again an alternative, that can we have this type of framework that can address these ongoing problems in current cosmology. Hubble tension is one of them, and also maybe some related with structure formation and so on.
Okay, thank you. Thank you.
Yes.
Yeah, I had a quick question. Do you have what's the estimated age of the universe in your model? Because there's some constraints from stellar ages and globular clusters, not really dependent on cosmology.
We have not tested yet with. We have just studied analytically. We have not tested with the data. So
no, but analytically, you can calculate the age or.
Yeah. Actually, yeah, we can calculate, yes. But we haven't yet done it. So
okay, fair enough. That's something to look at, because I think you need about more than 13 and a half gig a year to make it work.
Yes. Yeah, definitely.
Okay.
I would just want to make a sort of general statement on constructing models, right? So at least I can explain the way I tend to work, and that is that taking the evidence, so that dark matter is ruled out by the absence of the dynamical friction effect on various different tests. It's not just that one satellite test, but the bars and so on. This means that if I then want to construct an alternative model, it cannot be based on dark matter unless I can show that it nullifies this dynamical friction problem, right? And at the same time, the evidence is telling me that with MOND, I can solve the Hubble tension basically trivially, because that type of gravitational formulation, which is not ad hoc because it's basically it's already gauged on the rotation curves of galaxies, but applied to large scales, it forms these density structures which we see like El Gordo, KBC void, and solves the Hubble tension. So this is a strong indication that that's the direction to go. And so if one was to construct an alternative model, one would have to, on the one hand side, first demonstrate that it leads to the reduction of Chandrasekhar dynamical friction on dark matter halos, if there are dark matter halos in that model. And secondly, that it effectively leads to equations of motion which are Mondian. So through some coupling, say in the dark sector, but that those are strong conditions which today we have to fulfill. I just wanted to say that in general, that this I think should be done rather than just I mean, there are very strong constraints these days on any alternative model. We are not free to try any particular coupling. You have to demonstrate at least these two facts about your or properties of any alternative model.
Yeah. So it's more like effective field theory approach.
Yes, but you have to demonstrate. As I said, you have to have these two conditions.
Okay. Yes.
Yeah, so I mean, it's okay to suggest a model, say in a publication, but then in the next publication you should address these two issues. So, for example, if we are now developing a completely new model of cosmology, call it the Bohemian model of cosmology, it is necessary for us to also take into account the boundary conditions which is given by the observed CMB, which doesn't mean that the observed CMB has to be exactly what everybody else is saying, that it's the photosphere of the hot Big Bang, but a CMB has to be produced in the model. It might have a completely different physical origin, but it must be there, right? Because that's what we observe. So just as an comparison in the issues. The what?
The S.
Would the enhancement of structure growth on smaller scales like galaxy cluster also solve the cosmic sigmoid tension? That is there more power hidden in a small scale structure?
Yeah, so I can say something. So this actually originally goes back to Moritz Hasselbauer, who's some years ago suggested that in the MOND cosmological models we see these voids developing and then these overdensities, and in the voids there's just less matter, and then that has less fluctuations. And Indra Nil also pointed this out in a comment. This hasn't been actually quantified yet, right? But I think that's a very promising ansatz, and it makes a lot of it's intuition basically, right? The model is intuitively doing the right thing, but it has to be quantified. Mm-hmm. So I think the sigma 8 tension is not particularly severe thing. It's not something I would say, oh, I have no clue how to solve that. I think it's an automatic, it probably find an automatic solution, just like the Hubble tension is automatically solved because of the voids.
Yeah. And just to comment, this SH tension or sigma 8 tension has been found in the very, very local universe. So it would be consistent with the fact that we're in an underdense region. So I mean,
yeah, this is essentially what I was getting at. I think that's reasonable. This hasn't been quantified in detail, like how exactly it would work, but I think it's a reasonable thing to say.
Mm-hmm. Yeah, I mean that it has been studied up to, I think, 12 co-moving gigaparsecs, I think, or something like that. So like very local, and the void would be maybe up to 300 megaparsecs.
So the sigma 8 is generally only calculated up. I mean, okay, so in principle, your weak lensing probes any mass density along the line of sight. But as far as I understand, the technique is most sensitive to objects which are like halfway between us and the source, and the source is typically on redshift 1. So roughly speaking, you're most sensitive to like maximum redshift half, but probably less, maybe 0.3 or less. So yes, it is true that if we were in a local underdensity, that would reduce the S8, which is actually sigma 8 times square root of omega m. So yes, I think it's quite possible that if you're in underdensity, the locally measured value of S8 will not be the same as like if you were in an average density region or in an overdensity. That's possible. But I would agree with what Pavel was saying, though. The S8 tension is not yet statistically significant for LambdaCDM.